All right, so let's get started. So thanks for adjusting about Monday. There was, as you know, a job candidate, and he was having his research seminar from 3:30 to let's see, 3:30 to 5:30. He was having his presentation, and so I thought it would be good to reschedule the class. I still need to figure out when exactly to conduct this class, the Monday's class. But thanks for sending me your schedules. So let's get started. Recall that we're currently talking about conditional expectation. As we said, a conditional expectation, here the idea is the following. You're given a sigma algebra G. You can think of that as some sort of information that you have available to you. And you have some random variable X. And what you want to do now is you want to come up with your best guess of X given the information G. And that is what we'll be calling the conditional expectation of X given G. We made a formal definition of what this is. We also made a statement that conditional expectation exists and is unique. As usual in a measure theory course, when we say it's unique, we mean it's unique up to a set of measure 0. So two different people may find two different functions which work as the conditional expectation, but these two functions have to agree except on the set of measure 0. And then we started listing several properties of conditional expectations, and that's where we are. So let me go ahead and share the iPad screen. Let me first turn off the video. All right, is the iPad screen visible? Okay, by now, hopefully it should be. Yes, sir. Okay, thank you, Nandini. All right, so let's see where we are. So we're talking about conditional expectations. So I'm just going to take a couple of minutes to review a few things because it's been a few days. It's important that we are not lost. By the way, I have posted these notes on Google Classroom. So what do you have? You have a probability space omega fp. You have x in L1 of omega fp, right? So x is an integrable random variable. G subset of f is a sigma algebra that's given to you. You should think of G as information available to an observer. Okay, what we are talking about now is E of x given G. This is called the conditional expectation of x given G. And what you should interpret this as is you should think of E of x given G as best guess of x given the information in G. Okay, so we have to give a definition as to what is conditional expectation. We have to then show that conditional expectation actually exists, and so on and so forth. The tools we'll need are the following. The first is the notion of absolute continuity of one measure with respect to another. Once you have that, you can talk about something called the Radon-Nikodym theorem. That allows you to differentiate a measure nu with respect to a measure mu. You cannot do that for any measures at all. There have to be some connection between nu and mu. So we said we talked about what absolute continuity means. We said suppose we have omega f, which is a measurable space, and mu and nu, which are measures of omega f. We'll say that nu is absolutely continuous with respect to mu, and we'll write this symbolically in this fashion: nu absolutely continuous with respect to mu if whenever I have a measurable set with mu measure 0, then its nu measure also must be 0. That's what absolute continuity means. Now, one thing we saw earlier is that suppose I have f in L plus of omega, and I have a measure mu, and now I define a measure nu by nu of a set is the integral of f d mu over that set. One has checked that in this case, nu is absolutely continuous with respect to mu. So when you have an f and you define nu in this fashion, then nu ends up being absolutely continuous with respect to mu. Now you may ask the question, can you go in the reverse direction? Namely, suppose nu is absolutely continuous with respect to mu. Is it true that there exists such a function f with nu of a set being given by integral of f d mu over that set? And that answer is so basically they're asking the converse question. That question is answered by the Radon-Nikodym theorem in the affirmative. Okay, so suppose mu and nu are sigma finite measures on omega f, such that nu is absolutely continuous with respect to mu. Then Radon-Nikodym tells us there exists a non-negative measurable function f taking omega to 0 infinity such that Nu of any set is the integral of f with respect to mu over that set. Of course, this is only for measurable sets. Then we said that this function is unique in the sense that if g in L plus omega also satisfies these properties, then f and g must be the same almost everywhere. Then we said that this function f that you see here, we're going to give it a name. We're going to call it the Radon-Nikodym derivative of nu with respect to mu. Okay, and we'll denote it by d nu d mu. Okay, another term we said is, we said if d mu is f, we will say that nu has the density f with respect to mu. Then what did we do? What we did is we did not do the proof of existence. We said for a proof of existence, you can look at any of these books. There are many classics in real analysis and probability. You can look at one of them. Actually, any book on real analysis will do this. And of course, if a book on probability also does real analysis, they will also do it. We just did a proof of the uniqueness. We went over this. Then what did we do? Then we said that, so again, at this point, we have not yet defined conditional expectation. All we have defined is absolute continuity of measures. We have defined Radon-Nikodym derivative. We've stated Radon-Nikodym theorem. That's it. We haven't yet defined conditional expectation. So what is conditional expectation? And here's where we are. All right. So suppose omega fp is a probability space, and suppose x is an L1 of omega fp. So x is an integrable random variable. Let G be a sub-sigma algebra of f. In other words, G is a sigma algebra and it is a subset of f. Now, a random variable C in L1 of omega fp is said to be the conditional expectation of x given G, denoted E of x given G if the following two properties are true. First is that C should be G measurable. In other words, C should be measurable with respect to the sigma algebra, which corresponds to the information you have been given. The intuition behind this is that an observer who has the information G can compute C. That's what this means intuitively. The second thing that must be true is that for any A in G, and once again, G is the information given to you. For any A in G, it must be true that expectation of X indicator A is the same as expectation of C indicator A. Okay, and of course you can state this in terms of integrals. Now, such an object does exist, but it is unique only up to a set of measure 0. That's why we have this extra phrase here. C is called a version of, because there will be many versions of the conditional expectation. Okay, so notation is above. Conditional expectation, if it exists, is unique in the sense if C is the conditional expectation and zeta is the conditional expectation, then C and zeta are equal almost surely. This we have proved. So this means that C and zeta are both versions of the conditional expectation. All right. Then what we did is we proved that conditional expectation exists. I will not go over the proof of this. This involved Radon-Nikodym theorem. So we said suppose omega fp is a probability space. We said suppose X is an L1 of omega fp, and suppose G is a sub-sigma algebra of f, then E of x given G exists. Okay, so this argument involved measures restricting them to the sigma algebra G. I will not go over this again. But now we want to talk about the properties. Since we're going to talk about the properties, let me just go over this one more time. Let omega fp be a probability space, and suppose X is an L1 of omega fp. Let G be a sub-sigma algebra of f. So G is the information available to you. We want to define E of x given G. So we will say that a random variable C in L1 of omega fp is said to be a version of the conditional expectation of x given G, which is denoted E of x given G if two things are true. First of all, C has to be G measurable. In other words, whatever the conditional expectation is, it has to be measurable with respect to the sigma algebra, which is the information given to you. Now, remember that G is a smaller sigma algebra than F. So if C is G measurable, C is definitely going to be F measurable. There is no problem there at all. Okay. So C will always has to be F measurable. We're not even considering things which fail F measurability. right? But what this is saying is something stronger. Remember, if I make the sigma algebra on the domain smaller, okay, if I make the sigma algebra on the domain smaller, measurability gets more difficult. If I make the sigma algebra on the domain bigger, then measurability becomes easier. Okay, so remember, G is smaller than F. So C being F measurable is going to be there, there's no problem. But what this requires is that C should also be G measurable. Okay, and the second property is that for any A in G, expectation of X indicator A is the same as expectation of C indicator A. All right, so without further ado, let's come back to these properties. Right now, as I mentioned that in my notes, I have quite a few of these properties, and I could list all the properties at once, and then we could systematically work our way through them. But I think it'll be better to just write down a few first. Let's work our way through this, and then we'll add some more. Okay, so this is not complete. Okay, there are going to be more properties coming. All right, so what does this proposition say? Suppose omega fp is a probability space. Let G and H be sub-sigma algebras of F, and let X and Xn, n going from 1 to infinity, be integrable random variables on omega fp. Okay. So remember, if you're not dealing with integrable random variables, you cannot even go ahead with this discussion. All right. So when you're starting this discussion, all random variables have to be integrable. There is no choice. All right. So now let's first start with these four properties. Once we're done with them, we'll try and prove some more. Okay. So the first one says the following: if C is any version of E of X given G, then E of C equals E of X. So what does this mean? Okay, one thing I said, which maybe is just worth rewriting. Let me just write it up here. Okay, the reason I'm writing this is because when you study conditional expectation and undergraduate probability, you're typically taking conditional expectation of a random variable given some event or given some value of some other random variable. And you're not usually doing conditional expectation of a random variable given a sigma algebra. As a result, what you see in undergraduate probability, the conditional expectation ends up being a number. That is not the case here. The conditional expectation of a random variable ends up being another random variable. Of course, in some cases, it may happen that the conditional expectation of a random variable ends up being a number, but typically it ends up being another random variable. Anyway, this is just worth remembering. All right, so let's come back here. So what are we saying? If C is any version of E of X given G, then EC equals EX. That means the conditional expectation and the original random variable both have the same mean. Okay, so let's see why this is true. All right, so let's start with one. So suppose C equals E of X given G, right? So what do we know? We know that two things are true. The first thing we know is that C must be G measurable. That we are not going to need in this part. The second thing we know is the following. We know that for all A in the sigma algebra G, we have expectation of the X indicator A equals expectation of C indicator A. Right? This is part of the definition of conditional expectation. And now you say, wait a second, G is a sigma algebra. So G is definitely going to contain the whole set, which is omega. So I can take A to be omega. So this is true for all A in G. In particular, taking A equals omega, and of course, remember, if A equals omega, then the indicator of A is simply the number 1. That is it. or rather it's just the function. Actually, let me write it this way. This is just the function 1 everywhere on omega. But taking a equals omega, we get E of x equals E of c. Okay, so very straightforward. This just follows from the definition, but for the special case when A is the whole of omega. So that's the first property. The random variable x and any version of its conditional expectation have the same average. All right, then what is the second property? The second property is that if x is already G measurable, okay, then E of x given G is x itself. Okay, so what you're saying is that suppose x already is G measurable and somebody asks you to find the conditional expectation of x, you can just take it to be x. Now you can see why this is true, right? Basically, if x is G measurable, that intuitively that means anybody who knows G already knows x, right? Because we're taking this view. X is measurable with respect to a sigma algebra means intuitively anybody who knows the sigma algebra knows what the random variable is. So if x is G measurable, that means anybody who knows G already knows x. Well, if they already know x, then their best guess of x given G is just x itself. That's the intuition behind number 2. Let's see why this is true. Okay, so let me ask you a question. Let me actually not ask you a question. Let me just make a statement here. Let's come back to this definition of conditional expectation. So, suppose for the time being, I cancel this. I'm going to undo this, by the way. Okay. Suppose for the time being, I cancel property number 1, and I only require property number 2. Remember that C equals X will always satisfy property number 2, no matter what. Let me repeat that. Taking C equals X will always satisfy property number 2. There is no doubt at all. But that doesn't mean X is the conditional expectation of X. However, if property number 1 is automatically satisfied, that is, somebody tells you that X is already G measurable, then X and C are the same. So what is the moral of the story? The moral of the story is that if you look at just property 2, you can force it to be satisfied by taking C to be X. Now, of course, in order for X to be the conditional expectation, you also need property 1 to be true. So if you already know that X is G measurable, then X will be its own conditional expectation. The point I'm trying to make is that property 2 can be satisfied by making C equals X. But X may not be G measurable, which is why X may not always be its own conditional expectation. However, in this case, I'm telling you that X is G measurable. In other words, I'm telling you that X already satisfies property 1. Well, and you know that X always satisfies property 2. So that's the idea here. Any questions with what I'm, blabbering here? Or is that clear what I said? I will write it down, but is the idea clear? The point is, if I take C equals X, property 2 is going to be satisfied. There's no problem. All you need for X to be the conditional expectation is for property 1 to be satisfied. And what you're saying here is exactly that. Suppose X is G measurable. In other words, suppose property 1 is satisfied. All right, anyway, let me just briefly write down what I want to say here. So note that since E of indicator A, X, equals E of, I feel even silly writing this indicator A X for all A and G, X itself works as E of X given G whenever X is G measurable. And that is exactly what this this part of the proposition is saying. It is saying that if X is G measurable, then X is the conditional expectation. All right, so this basically works because C equals X always satisfies property 2 in that definition. All that's needed is property 1. And here property 1 is being given to you. Okay. Any questions with this? All right, now let's look at property 3. Property 3 says that linearity holds for conditional expectation, right? So it says that suppose alpha 1, alpha 2 are scalars, and I take alpha 1 x1 plus alpha 2 x2, and I take its conditional expectation. That is alpha 1 conditional expectation of x1 plus alpha 2 conditional expectation of x2. Note that here we're just using 1 sigma algebra. Okay. All right, so let's show this. So let alpha 1, alpha 2 be real. We have already said that we have already introduced this notation, right? So whenever we need, we have an infinite sequence of integrable random variables available to us. Okay, so we want to show that E of alpha 1 x1 plus alpha 2 x2 given G equals alpha 1 E of x1 given G plus alpha 2 E of x2 given G. All right. So in this case, this is kind of one of the first times we're doing it. So I'm writing it out explicitly. We want to show that E of alpha 1 x1 plus alpha 2 x2 given G is alpha 1 E of x1 given G plus alpha 2 E of x2 given G, P almost surely. Now, why is P almost surely there? Well, this is a random variable. This is a random variable. This is a random variable. And you know that when I say that this and this are the same, what I really mean is that they are the same almost everywhere. In other words, they are equal almost surely. So here I've explicitly said P almost surely. We may not always write this, but it is understood. Okay, so whenever you have a random variable here and a random variable here, you should, at least as far when you're doing conditional expectations, you should always keep in your mind that maybe the almost surely is there and it is being understood and it is not being said every time. Okay. Okay, so this is what we want to show. So what do we need to show? Basically, we need to show that the right side is G measurable. Second thing we need to show that if you look at the right side and you take any set A in G, expectation of the right side indicator A is the same as expectation of this guy indicator A. All right. So let's do the following. Let's make our writing a little easier. So let C equals E of x1 given G. Or actually, let C1 equals E of x1 given G. Let C2 be E of x2 given G. Right? We're just simplifying our notation a little bit. So C1 and C2 are just versions of the conditional expectations of x1 and x2 respectively. Okay, so what do we want to do? We want to show E of alpha 1 x1 plus alpha 2 x2 given G is alpha 1 C1 plus alpha 2 C2. Again, this is one of the first times, so I'm going to write P almost surely, but we won't always write it. Okay, so now what do you need to do? You need to show that this guy is G measurable. That's the first thing, right? So now note that C is E of x1 given G, so C1 is G measurable. Similarly, C2 is E of x2 given G, so C2 is G measurable. So clearly, C1, C2 are G measurable. Right, why is that true? Because C1 is already conditional expectation of x1 given G, and C2 is already conditional expectation of x2 given G. And hence, so is alpha 1 C1 plus alpha 2 C2. Okay, so the right side, alpha 1 C1 plus alpha 2 C2 is G measurable. So we have taken care of the first thing in definition of conditional expectation. Now we want to take care of the second thing. All right. So now let A in G. Right, so what do we want to show? We want to show that expectation of indicator A, alpha 1 x1 plus alpha 2 x2 equals expectation indicator A, alpha 1 C1 plus alpha 2 C2. Do you guys agree with this? If I want to show that the conditional expectation of this fellow is this guy, then I need to show that for every A in G, expectation of this guy times indicator A is the same as expectation of this guy times indicator A. And that's exactly what I've written down. Okay, so now let's start with the left side. Now, expectation of indicator A, alpha 1 x1 plus alpha 2 x2. What is this going to be? This is going to be expectation indicator A, alpha 1 x1 plus expectation indicator A, alpha 2 x2. Why can I do this? I can do this because remember that x1 and x2 are integrable random variables. So alpha 1 x1 plus alpha 2 x2 is also integrable. Actually, alpha 1 x1 is integrable, alpha 2 x2 is integrable. So when I'm adding two integrable random variables and taking the integral, I can just take the integral separately and then add, and that's exactly what I'm doing here. Okay, then I can do the following. Now I can say that this alpha 1 is a constant, I can pull it out. This alpha 2 is a constant, I can pull it out. So this is alpha 1 expectation indicator A times x1 plus alpha 2 expectation indicator A times x2. But wait a second. This is going to just be expectation indicator A C1, right? Because C1 is the conditional expectation of x1 given G. And this is going to be EF indicator A C2. Again, the reason is that C2 is the conditional expectation of x2 given G. And so we're done. So this gives us alpha 1 EF indicator A C1 plus alpha 2 EF indicator A C2. And now again, we use linearity in reverse, if you like. So this is going to be expectation of indicator A, alpha 1 C1 plus alpha 2 C2. And this is exactly what we wanted to prove. Right? So we have shown that linearity holds when you're talking about conditional expectations. Any questions so far? Questions? All right. Now let's come back to part 4 in the proposition. We'll prove that, and then we'll add 5, 6, 7, and so on and so forth. Okay. All right. So what does number 4 say? Number 4 says that if x greater than or equal to 0, then E of x given G greater than or equal to 0, P almost surely. You can express this in words. You can say that if a random variable is non-negative, then its conditional expectation is also going to be non-negative. This makes sense. Conditional expectation is your best guess of the random variable given some information. Now, if the random variable is already non-negative to begin with, then its best guess is also going to be non-negative. And of course, at this point, we remind ourselves that all these statements are typically made P almost surely. But that's what this is saying. If I have a non-negative random variable, its conditional expectation is non-negative. All right. So now let's prove 4. So suppose x greater than or equal to 0. By the way, I'm not going to write this all out, but this is true. If in this proposition, instead of x being greater than or equal to 0, x was just greater than or equal to 0 almost surely, then the result would still stand. Okay. All right. So suppose x greater than or equal to 0. And now let C be a version of E of x given G. Right? We want to show that C is greater than or equal to 0. We want to show that C greater than or equal to 0, P almost surely. All right, so let's do the following. Let's look at this set where C is negative. Okay, if the set where C is negative is empty, then that is fantastic. That means C is never negative. That's great. Otherwise, even if we can show that the set where C is negative has measure 0, our job is still done. So let's do that. Let's look at the set where C is negative and show that that set has probability 0. So let N be the set of all omega in omega such that C omega is less than 0. Okay. Now note that what is N? N is C inverse of minus infinity 0. Okay, and remember C is a measurable function. So under a measurable function, inverse image of a measurable set is going to be measurable. But remember, C is always F measurable, but something stronger is true. C is G measurable. So this set, of course, it's an F, but something stronger is true. This set actually belongs to G. So note that this thing is an element at G. Okay, and this is because, let me just write this, because C is G measurable. All right. Okay, now what do you have? Now, expectation indicator N times C is less than or equal to 0. Now, let's see why this is true. N is the set of points where C is negative. Okay, so suppose this indicator of N is 1, then C must be negative, and so the product must be negative. If the indicator of N is 0, then no matter what C is, this guy must be 0. In other words, this guy is always non-positive, and so its expectation must be less than or equal to 0. So that's the reason. Right? It's always non-positive. It can be 0, it can be negative, but it can never be positive. So expectation indicator N C is less than or equal to 0. Now remember, this N belongs to G. And so expectation indicator N of C is going to be the same as expectation indicator N of X. All right. So since E of indicator NC equals E of indicator NX, we have expectation indicator Nx less than or equal to 0. Right? But wait a second. But since X is non-negative, we must also have E of indicator n x greater than or equal to 0. Okay, so basically what I'm going to argue here is that expectation indicator n x is 0. How am I going to do that? Let n be the set where c is negative. Okay, note that n belongs to G. Now, what do I know? I know that expectation indicator nc is less than or equal to 0. Why do I know this? Because this function is always non-positive. Now, two things are true. Okay, the first thing is that x is given to be non-negative. So if I multiply x by an indicator, that will still be non-negative. And so its expectation is also going to be non-negative. So that is one fact that's true. Since x is non-negative, indicator nx is non-negative, expectation indicator nx is non-negative. On the other hand, we also know that since n is in G, since x, so this is true because x is non-negative. This is true because C is the conditional expectation of x. So let me just put that in some color. So this is true because x is greater than or equal to 0. So this thing that I just marked, this has no connection with x being conditional expectation. This just follows from the fact that x is non-negative. This part is true since C is E of x given G. All right, so by non-negativity of x, we have expectation indicator and x greater than or equal to 0. Also, since C is E of x given G and n belongs to G, we have expectation indicator and C is expectation indicator and x. And since expectation indicator and C is less than or equal to 0, expectation indicator and x less than or equal to 0. So what do you have? You have that this quantity is less than or equal to 0 and it is greater than or equal to 0. So it must be 0. So expectation indicator n x is 0. But wait a second. Expectation indicator n x is the same as expectation indicator n c. Hence, expectation indicator n c equals 0. Any questions so far? All right, so now what can you say? So now, indicator n times c is a non-positive function with expectation 0. So what that means is it must be 0 almost surely. All right, you have seen this sort of thing, okay? So remember, when we studied integration, I don't want this color here. No, I don't want that color there either. Okay, when we studied integration, you saw this. If the integral of f d mu is 0, if f greater than or equal to 0, and integral f d mu equals 0, then f is 0 almost everywhere. Right? Now, of course, multiplying by -1, the following statement should also be true. If g less than or equal to 0, and integral g t mu equals 0, then g equals 0 almost everywhere. Do you guys agree with this? That's exactly what we're using here, okay? The role of G is being played by this guy, all right? So you have seen a result like this, except it was stated for non-negative functions, and it was stated that if you have a non-negative function, you integrate it, you get 0, then the function must have been 0 almost everywhere from the beginning. And of course, multiplying throughout by -1, what you get is that if you have a non-positive function, you integrate it and get 0, then the function must have been 0 almost everywhere from the beginning. And that's exactly what we're using here. Okay, so where are we? All right, so indicator then C equals 0, P almost surely. So what does this mean? This means that indicator N equals 0, P almost surely, i.e. P of N is 0. Okay. Any questions with this? Questions? All right, so that takes care of properties 1 through 4 in the proposition. So let's continue the proposition, add a few more properties. I will not repeat all the notation. I hope that's okay. Okay, so there's the proposition continued. All right. So number 5 says the following. So number 5 basically gives you a monotone convergence theorem for conditional expectations. Okay, so let's write this down. Actually, what I'm thinking is that I'll just mix it up from my notes. In my notes, I have number 5 and number 6. Number 5, actually might as well just write it this way. I was just going to change number 5 and 6. It doesn't matter. Let me just follow my notes. Okay, so number 5 says the following. So if xn, n going from 1 to infinity, and x are non-negative, integrable random variables with xn increasing to x. By the way, is everyone on board with what this symbol means? Okay, so what this symbol means is that, does anyone want me to repeat it? Xn increasing to x means x1 less than or equal to x2 less than or equal to x3 dot 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 less than or equal to x, and x is the supremum or the limit of the xn's. Okay, so with xn increasing to x, then E of xn given g increases to E of x given g, P almost surely. All right. Now again, at some point I'm going to stop saying this P almost surely, but here I'm talking about a sequence of functions increasing to another function. So basically you're saying if xn increases to x, monotone convergence theorem tells you that the expectation of xn increases to expectation of x. But remember, expectation of xn is a number, expectation of x is a number. What you're saying here is that the conditional expectation of xn given g increases to conditional expectation of x given g. Now these two guys are functions, that's why this P almost surely is there here. Right, let's take property number 6. All right, so property number 6 says the following. So if H is a subset of G, remember G and H are both sigma algebras, all right? We may not say it every time, but G and H are both sigma algebras. If H is a subset of G, then E of x given G given H is E of X given H, P almost surely. All right, so what are you saying here? H and G are sigma algebras, and H is a smaller sigma algebra. Okay, so H is a subset of G. What you're saying is if you take X and you condition with respect to the bigger sigma algebra, and then you condition with respect to the smaller sigma algebra, the result is what you would have gotten if you had not bothered to do this step, and if you had just directly taken E of X given H. Okay, so this is an important property. This property is called iterated conditioning for obvious reasons. Iterated means repeated. This tells you what happens when you're doing repeated conditioning. All right, so what is this saying? This is saying that H is a subsigma algebra of G. I have my random variable X. If I take the conditional expectation with respect to G, and then I take the conditional expectation with respect to a smaller sigma algebra H, then the answer I will get is what I would have gotten if I had not bothered to do the step and just taken E of X given H. Now, of course, for this to hold, H has to be sitting inside G, all right? So if H is not sitting inside G, then this is not necessarily true. All right, so let's prove this. All right, so let's start here. So proof. Maybe I should try to continue it again, but I think it's understood this is just continued. Right? So let's start with number 5. Okay, let me actually make this comment here because this is important enough. So this is a monotone convergence theorem for conditional expectations. Right, monotone convergence theorem for expectations you already have. You automatically have that because expectations are just Lebesgue integrals. So if you have monotone convergence for Lebesgue integrals, you have it for expectations. This is for conditional expectations. Okay. Now let's come to number 5. All right. So suppose xn, n go from 1 to infinity, x are non-negative integrable random variables with xn increasing to x. Okay, so what do we want to show? We want to show that E of xn given G increases to E of x given G P almost surely. All right, so let's start by cleaning up our notation a little bit. Okay, so let yn be E of xn given G. All right, now remember, xn is non-negative, and we saw in one of the earlier properties that if I take conditional expectation of a non-negative random variable, then I'll get something which is non-negative. Okay, so since yn, actually, since xn greater than or equal to 0, we have, let's see which property it was. I think it was number 4, right? Yep, it was number 4. We have by 4 that yn is greater than or equal to 0. Right? Okay, again, this is true P almost surely. Right? Okay, what else is true? Also, since xn plus 1 minus xn greater than or equal to 0, we have yn plus 1 minus yn equals E of xn plus 1 given g minus E of x given g. No, E of xn given g, sorry. Equals E of xn plus 1 minus xn given g. This is greater than or equal to 0. P almost surely. All right, so let's just take this apart. Okay, actually, let me take this. Yn plus 1 is E of xn plus 1 given g. Yn is E of xn given g. So yn plus 1 minus yn is E of xn plus 1 given g minus E of xn given g. Now here I'm using linearity, and this was property number 3. Okay, so property number 3 told me that I have a linearity for conditional expectations. That's what I've done here. Then I've also said that this conditional expectation is greater than or equal to 0. And I got that from the fact that xn plus 1 minus xn is greater than or equal to 0. So here again, I'm using property number 4. The property number 4 tells me that if my random variable is non-negative, its conditional expectation must be non-negative. So this is by 4. Okay. All right, so what do you have? Okay, so what do you have? You have that all the yns are non-negative P almost surely, and P almost surely yn plus 1 is bigger than yn. When I say bigger, I mean greater than or equal to. Well, I claim that in this case, the following is true. Thus, 0 less than or equal to y1 less than or equal to y2 less than or equal to dot dot dot. P almost surely. Okay, so if you want to convince yourself of that, you can do the following. All right. So you can say, first of all, yn greater than or equal to 0, P almost surely, right? So for each, well, we can talk about this right now. I just want to convince you that this is true, but we can go over it next time since we're out of time. So let me stop sharing there, and let me also stop recording.